Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tam from Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series for the BSc Physics Honors students. Now we go through the paper on the basic physics 2. The section which we are seeing is geometrical optics, and we have been seeing a series of lectures. We have been going through a series of lectures on geometrical optics, and in the concluding lecture, that is lecture number 10, the contents that we are going to have is a review of what all we have seen from the beginning in this chapter, starting from the Fermat's principle of least time. Then using the Fermat's principle, we showed that the laws of reflection and refraction could be explained, and then we obtained the expression for the transverse magnification of a spherically refracting surface. Then we derived the Lagrange and Helmholtz laws for magnification. We talked about the cardinal points which were introduced by Gauss to simplify the refraction occurring at different surfaces of a number of lenses which one will have in any optical system. And we saw the graphical construction of image using the so-called hypothetical cardinal points. Then we went through the deviation produced by a thin lens. Then we discussed about a combination of lenses, how the focal length of a combination of 2 or more lenses can be reduced to the focal length of an effective focal length of a single lens. The combination of lenses will give rise to the focal length of an effective lens. And then we talked about coaxial system of lenses. Then from thin lens we went to thick lens, and the formulae that we obtained for the focal length of a thin lens and for a thick lens, we will have a review. We will look at the formulae, and then we will try to work out some problems. The variation of focal length of the convex lens with respect to thickness, then again the cardinal points of a thick lens. Now we have been talking about geometrical optics. What is geometrical optics? Or otherwise it is called ray optics. Why it is called ray optics? Light is assumed to travel in the form of rays, straight line. So the rays of light that we have seen in the earlier lectures, when they are incident on a convex surface, on any surface. Now a plane surface in the case of reflection, or refraction, again a line separating, a surface separating air and glass. You are talking about the rays of light incident and reflected, or a ray of light getting refracted, and so we talked about rays. The rays will be traveling in straight line. These are ray optics. Now Sir Isaac Newton said light consists of corpuscles And of course, you all know by now whether the corpuscular theory is right or wrong, but according to Newton, light consists of packets of energy or corpuscles, and so-called he propounded the so-called corpuscular theory of light, according to which light will be traveling in the form of rays, light will be traveling in the form of straight line. So, it's called geometrical optics, because we came across number of similar triangles, and we were using those relations. Similar triangles is the one that we saw when we tried to arrive at the focal length or any other quantity that we talk about. Now, these things we come across a number of similar triangles. Now, because of the fact that light travels in the form of rays. Now, in all cases, light will not be traveling. In the case of rays, that means we will come across a number of phenomena in the next lectures onwards, wherein you find the ray optics or the geometrical optics completely fails. And so, the geometrical optics will hold good in the formation of images in the case of plane mirror, or in the case of concave mirrors, in the case of convex or concave lenses, as well as a system of lenses. And again, I should tell you another approximation which we made use of when we arrived at the Gauss formula or other formulae that we obtained. They all make use of paraxial approximations. That is, we make use of the fact that the light rays which are incident on a lens, you have got a lens here, the light ray which is incident, this is optic axis. The light ray is incident does not make a very big angle. The angle of incidence of the light ray on the surface is assumed to be very small, or in other words, the light rays are traveling almost parallel to the optic axis, right. That is, they are the paraxial, parallel to the optic axis, they are called the paraxial rays. So, the approximation that you have here by the paraxial approximation, as it is called, the angle subtended will be very small. Therefore, you can make sin alpha, that the alpha is the angle subtended by the light ray with respect to the surface. These angles will be very small, which allows us to make use of the approximation. You make sin alpha is equal to alpha, or tan alpha is equal to alpha. These are the things, the tangent of angle subtended by the light rays on the spherical surfaces. We made them to be equal to the angles themselves. Sin alpha was made equal to alpha. Similarly, tan alpha was made equal to alpha. These approximations one should have in mind when we are talking about the geometrical optics. So, in the geometrical optics, once again I should tell, it revolves around the fact the light beam travels in the form of rays, and you come across similar triangles. You take the lengths, the proportional lengths and so on. So, that is the geometry comes. That is the reason why it is called geometrical optics. Then another thing is you make use of invariably the paraxial approximation. And so, this is the review of what we have learned so far in the ray optics. As I told you again, these ray optics will hold good for getting images in the case of concave, convex or mirrors and lenses and so on, combination of lenses. But there are a number of phenomena which we are going to see in the lectures to come, where this ray optics completely fails or geometrical optics fails. So, the fact that or the idea that light travels in the form of rays is not acceptable, or it cannot be made use of to explain some of the phenomena. Then the question is whether the Newton's theory is wrong, and again, if light is not traveling in the form of rays, then what is the other possibility? What is the solution for the problem? So, from the ray optics, we have to pass on to what is called what is optics? From the ray optics, we pass on to what is called a wave optics. So, light is made up of waves and so on. From the next lectures onwards, we will make use of what is called wave optics. From geometrical optics, we go to the wave optics. Is that right? So, we talked about Newton's theory, Newton's corpuscular theory, and then Snell's laws and the Gauss ideas on cardinal points and so on. Now, these ideas hold good, as I told you, for many of the cases when the image formation and so on, some of the phenomena cannot be explained, as I told you. Then go to some other kind of optics that we call as the wave optics. Now, we have the review of the concepts in geometrical optics, that is what I have reviewed so far. So, as far as the contents of this lecture are concerned, a brief review of the concepts which are being used in geometrical optics, that is what we have been talking about. Then the Fermat's principle of least time, that we have seen already, the Fermat's principle of least time, using which we were able to explain the laws of reflection of light and laws pertaining to the refraction of light. At this juncture, I should tell you that apart from the principle of least time, you should have heard of, or you should be knowing, the path of least action. Now, we are talking about least time. As students of physics or students of science in general, whether you are in some other subject like electronics, where you talk of path of least resistance. Current tries to flow in a circuit through that path for which the resistance is minimum. That is not only applicable to current and also is applicable to human beings and animals. So, the path taken by any system will consume least resistance, right. The current flows through that part of the circuit from A to B instead of going through. So, current tries to flow through that path for which the resistance is least. It is applicable to water also, any liquid medium, any medium or any system, the path of least resistance, path of least action, the path of least time. So, the Fermat's principle of least time, these are the things that one should know. Any system tries to keep its energy as minimum, least energy. In any physical system, the energy should be minimum in order that it is highly stable. Then we will come across the Gauss formula. I will show once again the Gauss formula and the refraction at a thin lens, lens maker's equation, refraction at a thick lens, and a few problems for which the formulae will be given now. So, we talked about in the very first lecture the Fermat's principle, which states that light travels between 2 points along the path that requires least time as compared to nearby paths. That is, the time taken should be extremum. From Fermat's principle, one can derive the laws of reflection and similarly the law of refraction. This is the kind of law that you have in the case of reflection. You show that theta 1 should be equal to theta 2. The angle of incidence should be equal to angle of reflection. We made use of the Fermat's principle and we showed that theta 1 and theta 2 are equal. Then we go to the law of refraction, wherein we say that theta 1 is the angle of incidence made by the light ray with respect to the surface of a medium which has got a refractive index mu. So, n2 here and n1 here, the two refractive indices of the two media. This may be air, this may be glass or water. So, n1, n2 are the respective refractive indices, and the Snell's law states sine of theta 1 by sine of theta 2 will give you the refractive index of what? n2 with respect to n1. The refractive index of glass with respect to air, so you write mu g A. Mu g A means the light ray, that is the refractive index of the light ray for glass with respect to air. In the problems which we are going to work out, I will be using mu g A. Mu g A means the refractive index of glass with respect to air. Okay. The prefix will be A and suffix will be g between mu. So, now the Snell's law states that the refractive index of any medium, say water or glass, the refractive index of medium n2 with respect to n1 will be given by the ratio of the sine of the angle of incidence to the sine of the angle of refraction, sin theta 1 by sin theta 2. That of course, you read in an elementary level. So, sin theta 1 by sin theta 2 should be the value of n2 or mu. So, you have now the formulae that is used for refraction through a thin lens, which goes as mu 2 by v1 minus mu 1 by u to be equal to mu 2 minus mu 1 by r1. What is mu r1? R1 is the the radius of curvature of the surface of the lens. You got a lens here upon which the light ray is incident. For this surface, this forms part of a sphere. So, the radius of this sphere is the so called radius of curvature, that is your R1. Now, using this formula, let us try to work out the following problem. Refraction at a convex surface. Let us have a break at this point. Welcome back. This formula which I showed will be now made use of to solve the following problem. The problem is as follows. A concave spherical surface of radius of curvature 100 centimeter separates two media of refractive indices 1.50 and 4/3. An object is kept in the first medium at a distance of 30 centimeters from the surface. Calculate the position of the image. So, you have your object at a distance of 30 centimeter. Following the sign convention, u will be minus 30 centimeters and the r is minus 100 centimeter, and mu 1 and mu 2 have been given. Mu 1 is 1.50 and mu 2 is 4/3. Therefore, substituting the formula that I showed just now, mu 2 by v 1 minus mu 1 by u is equal to mu 2 minus mu 1 by r1. That is the formula that you have here. You take this formula and now you substitute for mu 2, that is your 4/3 divided by v, and you are asked to work out where the image will be obtained. So, that is the value of v should be obtained. U is known, u is minus 30 centimeter. So, it is a simple problem in which you have substitute for mu 2 4/3 by v minus 1.50 divided by minus 30. Mu 2 mu 1 values are given here, and now r is known. So, substitute all these values here, obtain the value of v. All the quantities are known excepting v. Now, v works out to be minus 27.58 centimeter. That is the place, or that is the position where you will be getting the image. That is what is being asked. Calculate the position of the image. That is what you will be getting here. So, now we pass on to another interesting problem. Small filament is kept at the center of a hollow glass sphere of inner and outer radii. Inner radius is 8 centimeter. You have got a hollow glass tube, nothing is inside. A glass tube is there, glass sphere is there, and the inner radius is 8 centimeter. The outer radius is 9 centimeter. The refractive index of glass is 1.50. Calculate the position of the image of the filament when viewed from outside the sphere. You know where is the filament kept? Filament is kept at the center, and you are asked to determine the position of the image of the filament itself. Object is at the center. For refraction, the first surface, mu 1 is equal to 1 and mu 2 is equal to 1.50. U is equal to minus 8 centimeter and r is equal to minus 8 centimeter. So, this is the problem that I discussed just now. You have got a filament at the center of a inside a glass chamber. The chamber is empty, right? The chamber is empty here. You have air here. This is the material that you have got, glass. The vessel is made up of glass. It is spherical chamber, and I showed OA as the inner diameter, OA, OB is the outer diameter, okay, 9 centimeter. Mu is 1.5 for glass. So, again using the expression that I showed earlier, mu 2 by v minus mu 1 by u is equal to mu 2 minus mu 1 by r. Substitute the values now. For mu 2, you have 1.5 divided by v minus mu 1 is 1.0, u is 8 centimeter. That is the diameter of the filament to the inner surface, the outer surface, right. 1.5 minus 1.0 by minus 8 centimeter. The radius of curvature is again r, is 8 centimeter. So, V turns out to be minus 8 centimeter. So, if the filament is here and this is the distance is 8 centimeter, then the image will be obtained on the filament itself. It means that due to the first surface, this is the first surface, right? This is the first surface, this is the second surface. What happens now? It means that due to the first surface, the image is formed at the center of the sphere. The image will be formed at the filament itself. You got the filament here, the image also will be obtained on the filament. You go to the second surface, right? The second surface, for which again the distance is minus 9 centimeter. Following the sign convention, your minus sign here. Again the filament to the outer surface 9 centimeter. Earlier the filament to the inner surface was 8 centimeter. Now it is 9 centimeter outside for the outer surface. Again substituting for mu 1 and mu 2, you get 1 by V is equal to 1.5 by minus 9 centimeter. So, that will be your 1 minus 1.5 divided by minus 8 centimeter. This works out to be minus 9 centimeter. What does it mean again? Now, the distance between O and B, if O is the center, O and B is 9 centimeter. So, the filament which is kept at the center, the image will be again obtained at the same distance 9 centimeter. That means, the image is obtained, the image obtained from the refraction experienced by the light ray from the second surface, the image is obtained again on the filament, right. For the second surface, the distance between the filament and the second surface is 9 centimeter. So, the image is obtained on the filament. Similarly, for the first surface also, the image is obtained on the filament. Okay. That there are the two things that we have with regard to this problem. So, we talked about the lens equation in the earlier lectures, that goes as 1 by V minus 1 by U is equal to mu minus 1 into 1 by R1 minus 1 by R2. For a lens, R1 and R2 need not be equal. The radius, because the way in which you make the lens, the exact values of R1 and R2 will not be equal. That is the reason why you got R1 and R2. Let us go to the focal length. So, this is called a lens maker's formula. 1 by F, the same formula here on the left hand side will be having 1 by F is equal to mu minus 1 into 1 by R1 minus 1 by R2. That is called a lens maker's formula. And we have two lenses, right. You have two thin lenses separated by a distance d. In such a case, you want to find out the effective focal length. You understand, the two thin lenses are there with focal lengths f1 and f2. The lens system should be thought of a single lens. The effective focal length of the lens will be, f will be, what is f? F is the effective focal length of the combination. When you have combination of two lenses, the focal length of the combination f will be f1 multiplied by f2 divided by f1 plus f2 minus d. D, as I told you, is the distance separating the two thin lenses. You got a thin lens here, another thin lens here, separated by distance d. Then f will be given by the expression that I showed just now, which can be simplified again as f is equal to minus f1 multiplied by f2 by delta, whereas where delta obviously refers to the expression that you got in the denominator. So, now we pass on to the behavior of a thick lens, or in other words the focal length of a thick lens, that is 1 by f is equal to mu minus 1 into 1 by r prime plus 1 by r double prime minus mu into mu minus 1 into t divided by mu into r prime or double prime. Now, look at the formula. Supposing, what is t? T is the thickness of the lens. So, if the thickness of the lens t becomes 0, obviously the last term will vanish. Okay? The last term which is containing t, if t is 0, 0 multiplied by anything is 0. So, this term vanishes. So, this reduces to or r prime or double prime or on r2, that reduces to the formula that we had earlier in the case of a thin lens. So, in the case of thin lens, you have the formula like this. So, that is obtained from the generalized formula that we have for a thick lens. Obviously, for a thick lens, the equation that you have for a focal length should be getting reduced to the one that you have for a thin lens. That is happening here when t becomes 0, when t is very small or t becomes 0, the last term can be eliminated. Only when t, mathematically speaking, t should be equal to 0, then only your expression will getting terminated to 1 by f is equal to mu minus 1 multiplied by 1 by r prime or r1 plus 1 by r double prime or r2. That is the formula that you have for a thin lens. Now, let us again go through the problem. As I told you, we got two media, glass and air, and water and air. Now, let me go through the problem. A convex lens of focal length 24 centimeter is totally immersed in water. The refractive index of lens, that is glass, mu is 1.5, and a convex lens of focal length 24 centimeter, it is immersed totally in water. Find the effective focal length. Find its focal length in water. You got oil immersion microscope, and therefore, something like oil, you got water, the lens is immersed completely in water. What is the effective focal length? So, the solution is obtained as follows. You got mu g A. Mu g A refers to the refractive index of glass with respect to air, the 1.5. Similarly, refractive of water with respect to air is 1.33. So, you have here the refractive of glass with respect to water will be refractive index of air with respect to water multiplied by refractive index of glass with respect to air. So, that will be refractive index of glass with respect to water will turn out to be 1.5 divided by 1.33. Okay. There are two media, glass and water. So, the refractive of glass is 1.5, water is 1.33. You know very well mu 2 1 will be mu 2 by mu 1, that is what I have written here. So, if you have got glass and water, the refractive of glass will be coming in the numerator, that water will be coming in the denominator, and so the refractive index of glass with water will be 1.125. Okay. Then the formula that you have here, the effective focal length, so you got 1 by f as mu minus 1 into 1 by r1 minus 1 by r2. Then you have the formula here, right. When the lens is in air, what happens? The second term you got here mu minus 1, okay, 1.5. When the lens is in air, the focal length is 24 centimeter. So, that is what I am having here. So, when it is in air, 1 by 24, because the focal length is 1 by 24, this is the formula that I have here. 1 by 24 will be mu minus 1 into 1 by r1 minus 1 by r2, that is the equation 1. Okay. It should be clear. When the lens is in water, the problem is when the lens is totally immersed in water, you are asked to determine the focal length. So, I do not know f, that is what I should calculate, and so I keep 1 by f to be equal to 1 minus 1.25 minus 1 multiplied by 1 by r1 minus 1 by r2. So, what is 1.125? That is the refractive index of glass with respect to water. That is what I had it here, right. Refractive glass with respect to water is 1.125, and so when the lens is in water, completely immersed in water, so in the place of 1.5 you will be having 1.125. Now, divide these two, you want to get f. So, obviously, f is the only unknown quantity. So, f by 24 will be equal to 1 by r1 minus 1 by r2 will be getting vanished, will be, you have both, you divide the two expressions, 1 by r1 minus 1 by r2 can be cancelled, will be getting cancelled. Therefore, you are left with only the bracketed expression 1.5 minus 1, similarly 1.125 minus 1. So, your f by 24 will be 0.5 by 0.125. That gets you the focal length of a glass lens kept completely immersed in a liquid medium such as any water, 1.33 is the refractive of water, as all of you know. So, that you assume here. So, your f becomes equal to 96 centimeter. So, the focal length of a lens kept in water medium turns out to be 96 centimeter. So, we will pass on to the summary of the this lecture that we had so far, the concepts and formulae in geometrical optics were discussed in this lecture. I gave you the expressions which have been used, which we have derived, have been given in this lecture. Using these formula, various quantities which are required were deduced. Using the above formulae, we have worked out some problems. In geometrical optics, the problems can be getting them the effective focal length, getting the effective focal length, and other things can be obtained, and that is what we saw in the lecture. And let me ask you the following things to be done, namely mention the basic principles used in geometrical optics, and then recall the various formulae which you come across in geometrical optics. With this, we come to the end of the section on geometrical optics or the ray optics. We will stop with the ray optics because there are a set of phenomena, as I told you earlier, which cannot be explained using the ray optics or geometrical optics. From geometrical optics, in the lectures to come, we will go to what is called wave optics, which alone will be able to explain the phenomena of interference, diffraction, polarization, etc. So, the wave optics is definitely different from the ray optics or the corpuscular theory, which was proposed by Sir Isaac Newton. So, we have to pass on to wave theory of light. That is what I will be doing in the lectures to come. Thank you.